Hi class, welcome back to the next video. This is chapter 1.6 in the calculus series. Today we're going to talk about rational functions. So rational functions are really closely related to polynomials because our rational functions for this section are basically a fraction where you have a polynomial in the numerator and a polynomial in the denominator. So all the things that apply to polynomials also apply here. So we're always interested in factoring. Right, that's always like the start of the problem. Whenever you have a rational function, the first thing you want to do is really try to just factor everything, right? And then from there, see what kind of algebra you can use to manipulate the situation. So today we're going to focus mostly on like how to graph these things. In the polynomial section, we didn't really talk about how to graph them too much, although a lot of the things that we do to graph rational functions are the same thing that we do for polynomials, right? So for polynomials, if I want to graph, I find the zeros, find the y-intercept, and I try to understand what the end behavior is, and then plot all those things, and I draw my function, right? Pretty much the same thing for rational functions, right? I want to find all of my zeros, the y-intercepts, the x-intercepts. The only thing is that we're not allowed to have zeros in the denominator, right? You can never have zero on the bottom. So those will be my vertical asymptotes. So then I want to figure out what those are as well, right? So we really just kind of consider the asymptotes that come with our functions, our rational functions. That's really what sets apart the difference between rational functions and polynomials as far as like trying to graph them and analyze them, right? So in this section, we're going to focus on these functions where the numerator and denominator are both polynomial functions, okay? The main thing that we want to focus on again is finding the zeros of the numerator because that makes our entire function zero, right? We want to focus on the zeros of the denominator because that is where our vertical asymptotes are, the lines that we are not allowed to cross at all, right? Kind of like a force field. You can get really close to those things, but we can't actually cross them, right? The zeros that are shared in common for P and Q are also the holes in my graph, right? Which we'll talk about later as well. I want to know what happens when I plug in 0. That's going to be my y-intercept, right? So if I plug in 0 for P and for Q, what happens? What do I get out? And that's going to be my y-intercept. Also, the degree of the numerator compared to the degree of the denominator also tells me quite a bit about what my function is going to look like, okay? So these are the 5 things I want to consider when I am trying to graph or analyze the rational function. For polynomials, I just needed the zeros of one of them, what happens when I plug in 0 for one of them, right? Because there's only P in this case, right? And what is the degree of P? So for a polynomial, I only really had to worry about 3 things, right? So the zeros, what happens when I plug in 0, and what is the degree? Because that really would tell me everything that I needed. For a rational function, there's more going on because I have a, something in the bottom, right? There's more to it going on than just the numerator, just a regular function, right? So I have to be concerned with what's happening in the denominator as well. So again, the zeros of the numerator are going to be the x-intercepts of the graph, and the shared zeros between P and Q, anything that's in common as far as the 0, are going to be the holes of this function, right? The zeros of the denominator are the vertical asymptotes, and the relationship of the degree between P and Q is going to be what determines the horizontal asymptotes, right? So if the numerator has a larger degree, the asymptote kind of takes on one form. If the denominator has a larger degree, the horizontal asymptotes take on a different form. If they're the same degree, then it's a different form, which we're going to actually talk about now, right? We call this the end behavior, right? We've talked about this a little bit before for other functions and polynomials and things, like what's happening in the long run as x gets really large or really negative. So let's say that P is a polynomial of a form that looks like this, and Q is a polynomial as well that looks like this. So the forms here are not that different. We're just have different coefficients, A's for P, B's for Q. The degrees are different, right? N and M. Maybe N is larger, maybe M is larger, maybe they're the same, right? But they're different values, possibly, okay? So we have to specify them in a general sense with different values. So we have M and N. So let's say that P is a smaller degree than q. So the numerator has a smaller degree than the denominator, right? So I have bigger stuff on bottom than I do on the top. Then what's going to happen is that my horizontal asymptote is going to be 0. Since the denominator dominates the function for really large values, when you have large things in the denominator position, it means you're very close to 0, right? We saw this before in the previous section. So for instance, 1 over 1 is 1, right? 1 over a million is something very, very small. So if I have very large things in the denominator, then I have actually very small values that get closer and closer and closer to 0 as time goes on. Same thing as if I plug in negative values, right? I'm still going to go to 0 because negative 1 over a million is still very, very close to 0, right? It just happens to be a negative value, but it's still a very small negative value, okay? If my 2 degrees are equal, then in the long run, neither function dominates, right? The numerator doesn't grow faster than the denominator does. The denominator does not grow faster than the numerator. They both grow at relatively the same rate when I plug in very large value. So what happens then is that the horizontal asymptote becomes the ratio of the lead coefficients of the two, right? So it turns into an over bm, right? So for instance, if the lead term was 2 on top and 7 on bottom, then the horizontal asymptote is 2 over 7. That means that as I go in the positive direction and in the negative direction, they both tend to go towards 2 over 7. Okay. Now, if the numerator is larger, then what happens is that my function is going to act like a polynomial. Because remember, when you have a fraction, you're really dividing stuff, right? 2 over 4 is 1/2, right? 1 divided by 2. So same thing with polynomials. If I have a 5th degree polynomial on top and a 4th degree polynomial on bottom, well, if I were to actually divide those, I'd end up with a linear expression. So in the long run, my rational function would behave like a line, right? It would start from the negative position and it would end at a positive position, right? It has the same behavior that a line does. If the difference between the two degrees is 3, then it acts like a cubic in the long run behavior, right? So the long run behavior when the numerator has a larger degree is that it acts like whatever that polynomial would be. Okay. So now let's talk more about asymptotes. So we have 2 kinds of asymptotes. Actually, we have 3 that we really deal with for rational functions, and that is we talk about the vertical asymptotes, which we talked about first, right? We talk about the end behavior, which is a horizontal asymptote if the degree in the denominator is larger or if they're the same, right? Then we have a horizontal asymptote. If it's larger, then we get a slant asymptote, which could be linear in nature. It could be quadratic in nature. It takes on all kinds of different forms, right? It really depends on what the difference between these values are. So, again, the zeros of Q are going to be the vertical asymptotes because they're going to be walls that we can't pass, right? As we approach these vertical asymptotes either from the left side or from the right side, my function is going to go to either infinity or negative infinity. I don't know which. It really depends on the function. And we have to kind of look at a value in between a 0 and that asymptote to really determine whether or not I'm going to stay positive or stay negative, right? So we have to check a value between our vertical asymptote and whatever zeros are on either side of that asymptote, right? So because I know that when I have a 0, I either cross or bounce off of the x-axis. So if my function has a 0 and then a vertical asymptote, and in between those two values, my function is positive, it's never going to become negative because there's no 0 between that last 0 and that asymptote. So if my function is positive, it's going to stay positive. And as it approaches the asymptote from that side, it will always be positive. So it's going to go to positive infinity, right? So in between a 0 and an asymptote, a vertical asymptote, we have to check the value, right? Check a value of some point in between those two things, And whatever the sign is of that point, positive or negative, is going to tell us whether or not our function goes to infinity or goes towards negative infinity, because it'll never cross the x-axis again, right, in between those two values. If the difference between my polynomials, the degree-wise, is 1, then we're going to have a slant asymptote. Okay, so it'll be a line. My function will approach that line in the long run behavior, and it'll just kind of get as close to that line as possible. It'll never cross a slant asymptote. Okay. If the degree is larger than that, right? Let's say the difference is squared. I'll actually have a quadratic asymptote. It's a little different. We're not going to concern ourselves too much with what happens in the large run behavior of these things. You know, when the degree is very, very large between them, we'll just kind of focus on our asymptotes, right? So the horizontal and vertical. A horizontal asymptote, by the way, we can actually cross those things, right? A horizontal asymptote is really just a long run behavior. What does my function tend to go when I plug in large values or really large negative values? It is not something, it's not like a vertical or slant asymptote where we can't cross it. We can cross a horizontal asymptote. We just can't cross the vertical or slant ones, right? So, if this value is larger than 1, right, then the result is going to be an asymptote that takes on the shape that we would have when we divide the two, right? So if the difference is 2, then I'm going to have a quadratic type of asymptote, right? If the difference is 4, I'm going to have an asymptote that takes on, again, a quadratic shape, because a 4th degree polynomial and a 2nd degree polynomial basically have a parabolic shape, right? So if p of x and q of x share a 0, then that 0 is a hole in our graph. A hole is just a point of discontinuity, right? It just means that that point just does not exist. But as I approach from either side, it does exist, right? Everything almost matches up except for that point. It's kind of like someone just took a little eraser and erased my line of my graph at that point. That's all that a hole is, right? So let's just go ahead and jump into an example where we'll just kind of demonstrate a bunch of these things. Now, really, in order to show all of the things that we talked about right now, I'd have to do like 3 different examples, because we'd really have to show what happens for an asymptote going to 0, an asymptote when the degrees are the same, and then what happens when the degree of the numerator is larger. Now, we're not going to do that again. This is just a review. I have a whole larger set of videos on this in the pre-calculus stuff if you want to dive deeper into this. Okay, so again, it's really just to refresh your memory on the basics of how this thing works. So right away, notice that for our example, it's 2 cubics, right? Which means long run wise, it should go to a horizontal asymptote of the ratio of the 2 coefficients, right? 2 over 1. So the horizontal asymptote should be 2. Now we're going to go through these things one at a time. So remember at the beginning here, we had 5 things of interest. We're going to go ahead and look at these things and what they mean for our graph. So first off, we're going to factor everything. Okay, factoring everything allows us to know the zeros of the numerator, zeros of the denominator, right? So here, you can see that we could factor by grouping because we have 2s and we have 8s, right? So, and there's 4 terms, really easy to split in half and just factor by grouping. So pull out a constant of 2, then I will finish my factor by grouping. So I can pull out a common x squared here and a common -4. You see we have a common binomial term, so I can pull out that common binomial term. And then here we have a difference of squares, so then I can factor the difference of squares. So my numerator is 2, x minus 2, x plus 2, x plus 1. Okay. My denominator looks like I can actually factor by grouping as well. If I pull out the common x squared term, let's see if that works. It does. So I can pull out a negative here and an x squared here, and then I have a common binomial term. Pull out that common binomial term, and I have a difference of squares again. So I have x minus 1 twice, 1 from here and this one, and then my x plus 1 term. So that's my numerator and denominator, you can see that I actually have a whole at x minus 1, and I have a vertical asymptote at x plus 1. So doing this allows me to see what my zeros are, any wholes that I have, and any asymptotes. Now, a whole is not an asymptote, right? So I do not have 2 vertical asymptotes, I only have 1, right? So now that I have this factored, I can identify all the things that I need to identify. My whole is at x equals -1, right? That shared 0 here. My x-intercepts are all the zeros on top besides the whole that I have. So that's -2 and +2, okay? And my vertical asymptote is at +1, right? So factoring helps me out a lot. It allows me to find most of what it is that I need to know, right? My y-intercept is found when I plug in 0 for x. So if I plug in, it's actually easier to see it on the non-factored form, because I plug in 0, all of this goes away and all of this goes away except for the 2 constant terms. So when I plug in 0, I'll get -8, right? -8 on top, 1 on bottom, so my y-intercept is at -8, okay? So on the y-axis. So in order to find the end behavior, I'm going to look at what's going on. So the degree is the same, so I actually have a horizontal asymptote, and it'll be the ratio of the lead coefficients. So n minus m is 0, they have the same degree. So the ratio is 2/1, so that means that y equals 2 is my horizontal asymptote. Next, I want to understand what are my vertical asymptotes. So we haven't talked about limits yet. We'll talk about that in the next chapter. But basically, I want to know what's happening as I approach my vertical asymptote from the left side and from the right side. Am I going to infinity or am I going to -infinity, right? So I already know that my y-intercept is -8, okay? And I have x equals 0 is a 0 between 0 and -2, right? So I know that between my 0 and my asymptote, okay, so I have 1 0 here at -2, and then I have my asymptote. So let's kind of go back here a little bit, right? So on the left side of my vertical asymptote is the 0, -2. On the right side of my vertical asymptote is the 0, 2. In between the 0 and my vertical asymptote is the point x equals 0. At x equals 0, I have a negative value, which means that I go to -infinity as I approach my asymptote from the negative side, from the left, okay? And I know this because it goes -2, then x equals 0, and then my asymptote. There's no zeros between -2 and my vertical asymptote, so I know that I have a negative value in between those 2 points, so my function will go to -infinity as it gets really, really close to x equals 1 from the negative side, okay? So that's what this is basically saying, right? So the graph stays negative and it's never going to cross the x-axis again, right? So my function goes to -infinity as my x values get close to 1 from the left side, from the negative side, okay? So I need to understand what happens from the other side, right, in between x equals 1 and x equals 2, right? So I'm going to try to find a point in between 1 and 2. I'm just going to check the sign of it, and that'll tell me if, as I approach from the positive side, from the right side, is my function going to go to infinity or -infinity as I get close to that x-intercept, right? So here, my 0 was 2, my asymptote is 1. A point in between those two is 1.5, right? Or 3/2. So I'm going to plug in 3/2 into my function. The easiest way to do that is to plug it in to this factored form here, okay? But I don't have to actually evaluate anything. I just need to look at the sign. So 1.5 is less than 2, so I'll have a negative. 1.5 is a positive and a positive, so this will be positive, and this will be positive, right? So I'm really just checking the signs, right? This will be positive when I plug in 1.5, and this will be positive as well, and it's being squared, so it doesn't matter, it'll always be positive. So I have positive, 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 and one negative value. So my numerator will be negative and my denominator will be positive. So again, what I'm doing is I'm thinking about what happens when I plug in 1.5. 1.5 is less than 2. So this will be negative. I end up with some negative value. It'll be, negative 1/2. But even if I didn't know what the value was, I just need to know is it positive or negative. So here it'll be negative. I'm plugging in a positive value with a positive value for this factor. So it's positive. Same thing here is positive. Same thing here is positive. And 1.5 is larger than 1. So I'll be left with a positive value. So there's only one of those things that's going to make it negative, right? So that's what's going on here. So when I plug in 3/2, the sign for this term will be negative. This one will be plus, 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 plus. So overall, I have a negative value over a positive value, right? So that means I will have a negative value. So that means that as I approach from the right side, right, from the positive side towards my asymptote, I'm going to go to negative infinity. Okay. So as I approach from the left to my asymptote, it'll be negative infinity. And as I approach from the right side, it'll also be negative infinity. So looking at my graph, let's plot my points of interest. So I know I have a 0 at -2. I know I have a 0 at 2. I know I have a y-intercept at -8. Okay, so all of those things I know. I know as I approach from this side, so in between, or I'm sorry, I know I have a y-intercept of, or a vertical asymptote, I'm sorry, of positive 1, right? So I could draw a little dashed line here. So, and I have a hole at 1. Okay, so I also have this hole being graphed here. So as I approach in between these two values, right, from my 0 to my asymptote, I have a negative value. I'm not going to just magically come up and cross here because I have no zeros here. That's how I know I stay negative, right? Between 1 and 2, I chose 1.5, and it says it's negative. So as I approach from this direction towards this line, I know that my function stays negative, because if in between here is a negative value, it's never going to come up to be positive because nothing crosses this axis again, because this is the last 0. So it's going to stay negative, right? So as I come from the left, right, I cross here because my 0, let's go to this factored form. Okay, just like with polynomials, this is a 0 with multiplicity 1. This is a 0 of multiplicity 1. That means it crosses the axis at both of these zeros, right? If it was a multiplicity of 2, it would bounce off the 0, just like a polynomial, right? It's two polynomials, so a lot of the behavior mimics that of a polynomial. So from here, it'll be the same thing. It'll be positive and it'll be negative here because it crosses the axis at 2, right? Long-term behavior, as I go this way, I approach 2, right? So it comes up, and it approaches a value of positive 2 as I plug in larger and larger negative values. Here it crosses 2, but it starts to settle towards 2 as I plug in very large values as well in the positive direction. Okay. Here you can see that we're going to negative infinity forever, and I will never cross this line. It does not way down here cross over this line. It will never cross this line, right? So again, note that my horizontal asymptote of 2 can be crossed, unlike a vertical asymptote or a slant asymptote, if I had one. It's very important, right, to understand that. If I wanted to be a little bit more accurate in my graph, as far as like doing this by hand, maybe I would set my function equal to 2 just to find out if there's ever a point when I'm equal to 2, right? So that's what I kind of do here. Is I set my equation equal to 2. I'll clear my denominators by multiplying both sides by, I could have cleared out the denominator. Here, I divided everything by 2 because my numerator here is all multiples of 2. So I could just divide the whole equation by 2. Then I'll clear out my denominator. So I'll multiply both sides times this x cubed minus x squared minus x plus 1. And then I'll just zero it out. I'll get everything on one side. Okay. And so once I zero it out, these x cubes cancel out. When I add, here we go. When I zero it out, I actually get this. I get 2x squared minus 3x minus 5. So when I factor this, it factors to x plus 1, 2x minus 5, which means that there are 2 points where I am equal to 2. One of them is at -1, right? And the other is at -5/2. But I know that -1 is a whole. So I'm not actually equal to 2 there. It's just a superfluous extraneous value, right? So my value is not equal to 2, but that is a whole in my graph. So I don't have to worry about that. Okay. But x equals -5/2 or 2.5 is where, okay, so 2.5, if you notice, that is when I'm equal to 2. All right. And that is our video. See you guys on the next one.